So in this video we have a definite integral of the square root of 1 minus x squared, and that factor could perhaps make you think how to do it. And I'd like you to perform the integral in two different ways. One is to calculate the integral directly, and the other is to think about what this would mean geometrically and work it out. So have a go with pen and paper, and then I'm going to give you a detailed solution and various comments. So see you in a few minutes. Okay, welcome back. And I'm going to start using geometry because that's by far the simplest way to calculate this integral. So on this slide, I'm going to start off by using geometry to calculate this integral. So we look at the integrand. Y is equal to the square root of 1 minus x squared. So therefore, y is positive because the square root is positive by convention. And if you square both sides, you will get y squared is 1 minus x squared, which rapidly turns into x squared plus y squared is 1. And this is the equation of the unit circle centered at the origin. But since y is positive, this integrand corresponds to the upper unit semicircle. So it corresponds to this from x is minus 1 to x is 1. Those are our limits. So our integral is going to be the area of between the curve and the x-axis. So it's going to be this area and this area added together. And we know the formula for the area of a circle is pi r squared. This is a semicircle. The radius is 1, so it's going to be a half of this with r is 1, so it's pi over 2. And that is our result for this integral. But on the next slide, what I'm going to do is to calculate the indefinite integral and then use it to obtain the same result using calculus. So let's move on to the next slide. So on this slide, what I want to do is calculate the integral again, but this time using a sign substitution. The reason we're using a sign substitution is the presence of a square root of this form, something positive minus x squared. And the reason why we use a sign substitution is because this factor, which is making the integral potentially difficult, will become simple if we rewrite x is the sine of theta. So let's see how that works. 1 minus x squared, if x is the sine of theta, is 1 minus sine squared theta. So this square root becomes the square root of 1 minus sine squared theta. But sine squared plus cos squared is 1, so 1 minus sine squared is cos squared. And the square root of cos squared theta is the modulus of cos theta, because the square root is by convention positive. So that looks a lot simpler, but it's about to become simpler again because we don't need the modulus. The reason being, if x is sine theta, theta is the arcsine of x. So theta is an angle, and the way the arcsine function is defined, theta is going to be between minus pi over 2 and pi over 2. And over this range of theta values, the cosine of theta is always positive. So the modulus of cos theta is going to be the same as cos theta for all the possible values of theta. Okay. When we make a change of variables like this, the formula we're using is this one. So we have some function that we want to integrate, and we rewrite x with respect to a new variable. Here we're saying x is sine theta, and then we just rewrite the entire integrand in that way. And here we've seen we get a beautiful simplification. The square root of 1 minus x squared just becomes cos theta. And then we insert by hand dx d theta, and I've written that here already. X is sine theta, so dx d theta is cos theta. So what we're going to have is, for our integral, is the integral of cos theta from here and cos theta from here, so cos squared theta. But this is a definite integral, so what should our limits be? Well, here x is minus 1. If x is minus 1, sine of theta is minus 1, theta is arc sine of minus 1, that is going to be minus pi over 2. So we put the limit here, the lower limit of minus pi over 2. And at the upper limit, we want the angle theta such that its sine is equal to 1. Theta is the inverse sine function, the arc sine of 1, and that is going to be pi over 2. That's the way the inverse sine function is defined. So now what we have to do is we have to integrate with respect to our lovely new variable cos squared theta from minus pi over 2 to pi over 2. To integrate cos squared, I hope you remember that we should use this double angle formula. The cosine of 2 theta is 2 cos squared theta minus 1. So cos squared theta is cos 2 theta plus 1, all divided by 2. So we're going to have a factor of a half, and I will just pull that in front of the integral sign. And we have, as I said, cos of 2 theta plus 1 when we take that over to there. Now, when we integrate this, we're going to get something like sine of 2 theta. Let's see how it works. Well, if we differentiate sine of 2 theta, we'd get cos of 2 theta. You don't change the argument. But then from the chain rule, you'd multiply by the derivative of 2 theta, and that would give you a factor of 2. And we don't want the factor of 2. There isn't a 2 here. So we just mop that up by writing a factor of a half there. And now if you differentiate that, you get cos of 2 theta. And the integral of plus 1 is just plus theta. We're now going to evaluate this at the upper limit, and we can notice something. The sine of 2 times pi over 2 is the sine of pi. Sine of pi is, of course, 0. At the lower limit, we're going to get the sine of 2 times minus pi over 2, so the sine of minus pi, and that is again 0. So this term here is going to vanish. It's not going to contribute to the integral. So what we have is we have a half times pi over 2 at the upper limit, minus, and then minus pi over 2 from the lower limit. So that's pi over 2 plus pi over 2. We're going to get pi. But don't forget there's a factor of a half multiplying everything. So we see that our answer is going to just be pi divided by 2. And that is our answer for the integral, and it agrees entirely with the result from geometry. Now, I've performed the integral using a sine substitution this way. On the next slide, I'm just going to do it again and just go through a slightly different approach to it using drawing a triangle. So we'll see that on the next slide. So on this slide, I'm going to perform the same calculation and just make a slight change in that I'm going to draw a triangle. So let's see what I mean by that. We look at the integral, we see this square root factor, something positive minus x squared, and we think we're going to need a sine substitution. And this is the formula that we are going to be using just as before. So we're going to be saying x is sine theta. If x is sine theta, we draw a triangle. Theta is the angle, and the angle here, its sine, is the opposite over the hypotenuse. And the easiest way to have the sine of theta is x is to say that this is x and this is 1. And then from Pythagoras' theorem, this means that this adjacent side is going to have to be equal to the square root of 1 minus x squared. So let's just verify that. Pythagoras' theorem says this squared plus this squared must be the hypotenuse squared. So if we square this, you get 1 minus x squared. You square this, you get x squared. Add them, the minus x squared and the x squared cancel. You're left with 1, and 1 is 1 squared. So the three sides of this right angle triangle satisfy Pythagoras' theorem. And if you're drawing a triangle, make absolutely certain that the sides satisfy Pythagoras' theorem. It's a very easy check. So, looking at the triangle tells you immediately that this is a good substitution to make, because the factor in the integrand, which is making life difficult, is one of the sides of the triangle. And as soon as you see that, you think this is almost certainly going to work. After that, it's really just the same as the previous slide. So what do? We write out our formula. X is sine theta, theta is arcsine of x, dx d theta is the cosine of theta, and from our triangle, we haven't had to do the algebra, you can just read off that the cosine of theta is the adjacent over the hypotenuse, so it's the square root over 1, it's the square root. So therefore, we can say that our integral is equal to the integral where we replace this, the square root, by the cosine of theta. We insert by hand dx d theta, that's another cosine of theta. And again, I've just changed the limits as before by saying if x is minus 1, theta is minus pi over 2. And if x is 1, theta is pi over 2. And then we've just used the double angle formula. So we've said that cos squared is a half times the cosine of 2 theta plus 1, and pull the half outside of the integral. The integral of cos 2 theta was a half sine 2 theta, and the integral of 1 is not 1. I've written something stupid. The integral is, of course, plus theta. Apologies for that. And then we just say, well, at the upper and lower limits, this term will vanish. And here we're going to get pi over 2 at the upper limit, minus this at the lower limit, where it's minus pi over 2. Minus minus is plus, so we get pi times a half, pi over 2, and that is our answer again. So on the previous slide, we performed this integral using algebra. And on this slide, as well as using algebra, we've drawn a triangle. And I personally like drawing triangles. I think it helps such calculations. Now, notice that on the last slide and on this slide, for the definite integral, what I did was I converted the limits here from limits on x to limits on theta. And what I want to do on the next slide is just talk a little bit about the indefinite integral and how we could go from this result back to rewriting it in terms of x. So we'll look at that on the next slide. So on this slide, I want to talk about the indefinite integral. And these three lines of algebra are ones that we had on the previous slide, and they led to this formula here, but between limits. Now, you could, in principle, say that this term is given in the following way. You know that the angle theta is the arcsine of x, so you could say that this is a half the sine of 2 times the arcsine of x. But that is horrible. It's really, really ugly. So please never think about doing that. Instead, what we want to do is to use the double angle formula and say the sine of 2 theta is 2 sine theta cos theta. And then the half here and this 2 will cancel, and our indefinite integral will become a half outside, open big brackets, sine theta cos theta from here plus theta. X is sine theta, cos theta is the square root of 1 minus x squared, and theta is arcsine of theta. So we can just write this answer down immediately, a half x root 1 minus x squared plus arcsine. And if you want to, you might consider using a triangle to help you again and just say, here we go. This is our angle theta, this is x, this is 1, this is root 1 minus x squared. So just looking at that, we can read off that the sine of theta is x over 1, opposite over the hypotenuse. The cosine of theta is the adjacent over the hypotenuse, so it's the root 1 minus x squared over 1. So we just have x times root 1 minus x squared. So again, I think drawing triangles is actually very useful. So on the next slide, I'm going to give you a couple of short exercises to look at. So the first exercise is just to use our result for the indefinite integral to calculate the definite integral, but now not having limits in terms of our new variable theta, but using limits with x, and again you will obtain pi over 2. And secondly, verify our result for the indefinite integral by differentiating it and showing that you regain the initial integrand, in other words the square root of 1 minus x squared. The more you differentiate results for integrals, the better you will become at differentiation and at algebra. And for this second exercise, I will put the solution on the next slide, but very much suggest that you try it before you look at that slide. Okay, let's have a look at the next slide. So this is what we have to differentiate. There's a factor of a half multiplying everything, so let's pull it through the derivative. Here we're going to be using the product rule. Differentiate this term first. You get 1 times the square root, and then we get x times the derivative of this. This is to the half, so we're going to pull a factor of a half in front. That's a 2 on the bottom. We reduce the power by 1, so we have 1 minus x squared to the minus a half. That's a square root on the bottom. And then we multiply using the chain rule by the derivative of 1 minus x squared. That's minus 2x. So there's a minus sign, there's a 2, and there's an x, but there was already an x there, so overall it's x squared. The 2 and the half will cancel. And finally, we have the derivative of arcsine to add to this, and that's something that one hopefully just knows. If not, try to rederive it. And that gives us 1 over the square root of 1 minus x squared. So we have 3 terms. You could put all 3 over this denominator and it will still work, or you can just put these 2 first of all over the denominator. I'll write this term first because it's positive, so I have plus 1 over the square root, and this term we have minus x squared over the square root. And now we look at the numerator and the denominator, and this is 1 minus x squared to the 1. This is 1 minus x squared to the half on the bottom, or effectively we're multiplying 1 minus x squared by 1 minus x squared to the minus a half. Either way, what this gives us is the square root of 1 minus x squared. So we have the square root of 1 minus x squared plus the square root of 1 minus x squared. So that's 2 times the square root of 1 minus x squared. And again, the half and the 2 cancel, and we are left with the initial integrand as we expected. So we see that the result for the indefinite integral was correct. With that, I'll stop this video.